Problem 1 on the practice quiz is to approximate the area underneath the given curve with two rectangles. In fact, this is not going to be a very great approximation, but it illustrates how we do this. If you look at the function f of x equal x squared between 0 and 3, you'll see that you have these points on the curve. And this is the f of x equal x squared. And we want to approximate the area under the curve. And it said do it with two rectangles. So if you're going to do it with two rectangles, you're going to split it here. And this point is 3/2. And it said to use an upper sum, which means you're going to overestimate the area. So the first rectangle looks like this in blue, and the second rectangle looks like this in blue. And the width of the rectangle is obviously 3/2. And the height of the rectangle, since the function of x is equal to x squared, this height would be 9/4, and this height would be 9. Notice that you figure that out by looking at the value of f of x at the top of each rectangle. And of course this would be 3 squared. So now we're ready to calculate the area. The area of the two rectangles would be the height of the rectangle times the width of the rectangle, which is 3/2. That's the first one. Plus the height of the second rectangle times the width of the second rectangle times 3/2. And you get 27/8 plus 27/2 equals 27/8 plus 108/8, which equals 135/8, which is equal to 16.875 is the area. Second problem is just to use sigma notation and follow the directions in the sigma notation to calculate a sum. And it's just going to be 4 terms in the sum. So for k equal 1, we get 2 sine pi, plus for k equal 2, 2 sine of pi over 2. For the third term, we get 2 sine of pi over 3. For the fourth, we get 2 sine of pi over 4. Sine of pi is 0, so this term is 0. The sine of pi over 2 is going to be 1. Sine of pi over 3 is going to be the square root of 3 over 2. And sine of pi over 4 is going to be the square root of 2 over 2. So if you sum that up, you get 0 plus 2 plus square root of 3 plus the square root of 2, which happens to be answer B. Problem 3, you have information about two integrals, and we want to find the value of a third integral. you're given that the integral from 2 to 6 g of x dx equal 12, and the integral from 2 to 9 of g of x dx equal to 16. And so you can see that the integral from 6 to 9 of g of x dx would be simply 16 minus 12 equal 4. Therefore, the integral from 9 to 6 of g of x dx equals minus 4. So the answer is A, minus 4. Problem 4, we want to find a definite integral. So with 0 to 4, I would rewrite this as 2 to the 1/2 power dx, and this would be equal to 2 x to the 3/2 divided by 3/2 between 0 and 4 equals 4/3 x to the 3/2 between 0 and 4 equals 4/3 x, 4 to the 3/2 minus 0, and that equals 32/3. And so the answer is D. And number 5, we have another definite integral we want to calculate. But first, it would be advantageous to go ahead and expand the integrand so it would be easier to integrate. So we write the integral is equal to the integral from 1 to 2, you get t squared plus 2 plus t to the minus 2, which is 1 over t squared, dt. Integrating this, we get t cubed over 3, that's finding the antiderivative, plus 2t minus 1 over t. And we evaluate this according to the fundamental theorem of calculus between 1 and 2. And so this equals 8/3 plus 4 minus 1/2 minus 1/3 plus 2 minus 1. And so we get 8/3 plus 4 minus 1/2 minus 1/3 minus 2 plus 1, and we get 7/3 plus 3 minus 1/2, and this equals 29/6, which is answer B. Problem 6, we need to use the fundamental theorem of calculus, and basically to calculate dy dx, we just simply need to evaluate, although I notice there is one issue here in this problem. This should be a t. We're integrating with respect to t, and to calculate dy dx, we simply substitute the x everywhere we see a t, as long as it's simply an x. So dy dx is simply going to be the square root of 10x plus 5. And that is answer C. One of the things I like to point out here, if this x, instead of being an x, had been some g of x, then we would have substituted g of x everywhere we saw a t, and then use the chain rule to multiply the result by g prime of x. Problem 7, we want to find the derivative of the integral. And here again we have to use the fundamental theorem of calculus. But notice the variable x to the fourth needs to be at the top end. So we need to rewrite this as y equal 0 to x to the fourth with a negative sign, cosine of the square root of t dt. Now we got two things. We need to substitute the x to the fourth everywhere we see the t, and then we need to take the derivative of x to the fourth with respect to x. So dy dx will be equal to minus cosine of the square root of x to the fourth times 4x cubed. We simplify this and we get minus 4x cubed cosine of x squared. And that is answer A. Problem 8 is another fundamental theorem of calculus problem. And dy dx will just simply be taking x to the 1/2 and substituting everywhere you see a t. And that would be e to the x to the 1/2 squared plus 1 times d dx of x to the 1/2. Need to use a chain rule here. So this is going to be equal to 1 over 2 x to the 1/2 times e to the x plus 1, which is answer B. Problem 9, we want to find the total area of the region between the curves, between the curve and the x-axis. If you look at this function, notice first of all that y is more than 0 for all x. Therefore, it's not dipping down below the x-axis. Well, it is 0 at x equals 0 and at x equals 2. But I think if you graph it, it will always be above the x-axis except at 2 points. And so we just have to do the integral to calculate the area. So the area would be equal to the integral from 0 to 2 of x squared times x squared minus 4x plus 4. We're just simply expanding this term. Multiplying this out, we get that the area is equal to integral from 0 to 2, x to the 4th minus 4x cubed plus 4x squared. Taking the antiderivative, we get x to the 5th over 5 minus x to the 4th plus 4x cubed over 3. We evaluate that 0 and 2, and we get 32 fifths minus 16 plus 32 thirds. By the way, this should be x cubed over 3 here. Always check your work. And so this becomes 96 fifteenths minus 240 fifteenths plus 160 fifteenths equals 16 fifteenths, which is answer B. Now we want to find the area of the shaded region here. Notice that the first region is below the x-axis, and so the integral would come out to be negative, so we'll take the absolute value of that part. The second region is above the x-axis. Notice we need to find, first of all, the point where it crosses the x-axis, and we set y equal to 0, which means the square root of x equals 3, or x equals 9. So this point is 9, x equals 9. So the area will be equal to the absolute value of the integral from 0 to 9 of x to the 1/2 minus 3 dx. The absolute value of that. Plus, we know that the second integral will come out to be positive, so we don't need to take absolute value. So we go from 9 to 16 of x to the 1/2 minus 3 dx. And so we get the area equals the absolute value of 2/3 x to the 3/2 minus 3x, evaluated between 0 and 9, plus 2/3 x to the 3/2 minus 3x, with limits 9 and 16. So plugging in, we get the area is equal to the absolute value of 18 minus 27. Notice that's going to be plus 9 after we take the absolute value, plus we get 1/28 thirds minus 48 minus 18 minus 27, and this is equal to 9 plus 1/28 thirds minus 48 minus 18 plus 27, and when you add all this up, you get 38 thirds. So the answer is answer A. Next problem is also one in which we want to find the area under the curve. Notice in this case, the complete curve is more than or equal to 0 everywhere. So the area would be equal to the integral from 2 to 4 of x minus 3 squared dx. And the antiderivative is pretty easy to calculate here. Just x minus 3 cubed over 3. You can verify by taking the derivative, and we evaluate between 2 and 4. And so plugging in, we get 1/3 minus a third equal 2/3. And the answer is B. Number 12, we have really what's called a differential equation, and we want to solve it by taking the integral, finding the antiderivative, and using the initial condition that y of 0 equals 2. So basically, if dy dx is given by this expression, then y would be equal to the integral of 12 sine square x cosine of x dx. So we want to take this integral and calculate the antiderivative. Here we would use a substitution that u is equal to sine of x, and du dx is equal to cosine of x. So du is equal to cosine of x dx. And you can see that this portion of the integral can be replaced by du. And u is equal to sine x, so the integral becomes 12 u squared du, which is equal to 4 u cubed plus a constant is equal to 4 sine cube of x plus a constant. Notice we just take u and replace it back. So replace sine of x back into u, and we get 4 sine cube of x plus a constant. Now, so this is a function for y. We're given that y of 0 is equal to 2, which means that 4 sine cube of 0 plus c equals 2. This implies that c is equal to 2. So the complete solution, having determined what the constant is 4 sine cube of x plus 2, which is answer A. Problem 13, we want to solve the problem. Basically, we want to find out what f of x is. And we're given that the integral from 1 to x of f of t dt is equal to this expression, a polynomial. And recalling the fundamental theorem of calculus, if we take the derivative of the integral, we will get f of x. So simply replace x everywhere you see a t. So we take the derivative with respect to x of the integral from 1 to x of f of t dt. That should also be the integral, or I'm sorry, the derivative with respect to x of 5x squared plus 9x minus 2. This is calculated by just substituting x where you see a t, and we get f of x, then equals the derivative of this expression, which is 10x plus 9. So f of x equals 10x plus 9, and we have answer A. Problem 4, we're going to use the fundamental theorem of calculus also, plus look at some of the information that's given. And it says that the function f has a positive derivative for all values of x, and f of 2 equals 0. Which of the following statements must be true of the function g of x? Well, let's look at this. We can take the derivative of g of x, and g prime of x would be simply equal to f of t. That's the fundamental theorem of calculus. Now, we're given that f of 2 equals 0. That means that f of 2 equals 0, and that's g prime at 2. So that says that g prime of 2 has a horizontal tangent. So it could be a max, local max, or a local min. Or it might not be either. It really depends on the concavity. So we need to look at the concavity. To find the concavity of g, we need to know the second derivative. Well, g double prime of x would be just f prime of t. And we're told that f has a positive derivative for all values of x. So f prime is then more than 0. So it's concave up, which means it's a local minimum. And at x equal 2. So the answer is A. By the way, just to keep things correct, this should be an X here. I'm not going to redo the video, but that should be an X. Problem 15 is to evaluate the indefinite integral. This is one of those examples where you can use a substitution. And as we've said in class, anytime you see an expression in an integral in which its derivative appears as a product of the rest of the integral, then you can probably use that as a substitution and be able to integrate the function. So if we let u equal x to the 6 plus 8, then we have du equals 6x to the 5th dx. Consequently, x to the 5th dx is equal to du over 6. Therefore, this portion of the integral is equal to du over 6. And the rest of the integral, we'll just apply the substitution. So the integral equals the integral of x to the 5th square root of x to the 6 plus 8 dx equals simply u to the 1/2 divided by 6 du after you make the substitution. And this integral is now u to the 3/2 divided by 6 divided by 3/2 plus c, and you can see that this is u to the 3/2 over 9 plus a constant. Substituting for u, we get 1/9 x to the 6 plus 8 to the 3/2 power plus a constant, and the answer is D. Number 16 is another indefinite integral in which we're going to use a substitution. Here, good substitution appears to be to let u equal 9 plus cosine of t, because du is equal to minus sine of t dt, which means that sine of t dt is equal to minus du. So this part is going to become minus du. And so the integral of sine of t over 9 plus cosine of t to the 4th power dt will equal minus the integral of 1 over u to the 4th du equals minus the integral of u to the minus 4 du, which equals minus u to the minus 3 over minus 3 plus a constant, which is equal to u to the minus 3 over 3 plus a constant. Substituting in, turning the u over, we get plus 1 over 3 times 9 plus cosine of t after we substitute in for u to the 3rd power, and plus a constant, and that is answer A. Have one last, well, it may not be the last substitution, but another substitution here. And this one is a little more subtle, except you got to remember something about inverse sines. The integral of inverse sines, or derivative of inverse sine. Notice you got e to the x here, and if you let u equal e to the x, notice that e to the 2x is equal to u squared. So if we let u equal e to the x, we've got du is equal to e to the x dx. So e to the x dx is going to become du, and e to the 2x will become u squared. So the integral of e to the x dx divided by the square root of 1 minus e to the 2x equals du divided by the square root of 1 minus u squared. Now you might remember that the derivative of inverse sine of u is equal to 1 over the square root of 1 minus u squared. So the antiderivative this is equal to inverse sine of u plus a constant. So this is equal to inverse sine of e to the x plus a constant, which is answer C. Number 18 is a little bit similar. One of the things to notice is that the derivative of the inverse tangent is equal to 1 plus t squared. And you have an inverse tangent right here. So let's think about using a substitution of u equal inverse tangent of t. So du dt is equal to 1 over 1 plus t squared. So du is equal to dt over 1 plus t squared. So we can see that dt over 1 plus t squared can be replaced by du, and we get that the integral of dt over 3 inverse tangent of t times 1 plus t squared is equal to 1/3 du over u. Remember 1 plus t squared. Remember u is equal to inverse tangent of t. So this integral is equal to 1/3 ln absolute value of u plus a constant is equal to 1/3 ln of the absolute value of what u is, which is inverse tangent of t, plus a constant. So the answer is C. Okay, now number 19 is going to require 2 substitutions. Notice that if you let u equals x cubed equal x cubed minus 7x, that you see its derivative right here. So let's try that and see where it leads us. We'll find out that we need to do another substitution to complete the job. If we let u equal x cubed minus 7x, we get du is equal to 3x squared minus 7 dx. That means that 3x squared minus 7 dx is equal to du. And then we replace u with x cubed. Well, everywhere we see an x cubed minus 7, x, we'll replace that with u. So doing the substitution, we get that the integral of 3 times 3x squared minus 7 sine to the 5th of x cubed minus 7x times cosine of x cubed minus 7x dx. After we do the substitution, we'll end up with 3 sine to the 5th of u times cosine of u du. Notice that the du was this part. So now we're faced with another substitution. We've got a sine to the fifth u cosine of u. So let's let v, another variable, equal sine of u. So dv equal cosine of u du. So cosine of u du is going to be dv. And v is going to be sine u, so this is going to end up being v to the fifth. So doing the substitution, we get 3v to the fifth dv is equal to 1/2 v to the sixth plus c. Well, v happens to be sine of u, so this is equal to 1/2 sine of u to the sixth power plus a constant. But u, you recall, is x cubed minus 7x. And so we get a final answer as 1/2 sine to the sixth power of x cubed minus 7x plus a constant. And that answer is A. Okay. Notice that if we let u equal what I call the more complicated term here, let u equal 2 plus cosine of theta, that the derivative of that is going to be minus sine of theta d theta. So du is going to be equal to minus sine of theta d theta. So sine of theta d theta is going to equal to minus du. So this part will become du. And as we do this, since this is a definite integral, we're going to change the limits of integration from integration on theta to integration on u. So we need to change this pi to 3 pi over 2 of sine of theta d theta over 2 plus cosine of theta. That's going to be equal to minus du over u, except u is going to go, since u is equal to 2 plus cosine of theta, u is going to go from 2 plus cosine of pi to 2 plus cosine of 3 pi over 2. Now let's go ahead and set the limits of integration. Cosine of 3 pi over 2 is going to be 0, so this is going to be 2. Cosine of pi is minus 1, so this is going to be 1. Minus integral of 1 over u du. So this is equal to minus ln of u, evaluated between 1 and 2, is equal to minus ln of 2 plus ln of 1. Of course, ln of 1 is 0, so the answer is minus ln of 2, which is answer A. Now, this particular problem is one in which we want to find the area between two curves, and we want to find the area shaded in that's shaded here in blue. And notice we want to take the function on top, which is f of x, minus the function on the bottom, which is g of x. And we want to take the area. It's equal to the integral from -4 to 0. F of x minus g of x dx. So the area is equal to -4 to 0 of x cubed plus x squared minus 6x minus 6x dx, and this is equal to -4 to 0 of x cubed plus x squared minus 12x. Doing the integration, we get that the area is equal to x to the 4th over 4 plus x cubed over 3 minus 6x squared. Evaluate between -4 and 0, and we get 0 plus 0 minus 0 minus, plugging into -4, we get 256 over 4 minus 64 over 3 plus 96. And this is equal to 96/12 over 12 minus 256 times 3 over 12, getting the lowest common denominator for each one of these, plus 64 times 4 over 12. You add all this up and you get 640 over 12, and so the answer is B. Number 22 is, we have to look and see what the top function is. Top function looks like it's equal to x squared minus 4, and the bottom function is equal to 2x squared plus x minus 6. So the area is going to be equal to integral from -2 to 1. And by the way, you need to find where these curves intersect, and you find out that they intersect at x equal 1 and x equal -2. That's why we want to go from -2 to 1 of the top function, which is x squared minus 4, minus the bottom function, which is 2x squared plus x minus 6 dx. So this equals the integral from -2 to 1 of minus x squared minus x plus 2 dx equals minus x cubed over 3 minus x squared over 2 plus 2x. Evaluate between -2 and 1, And plugging this in, you get minus 1/3, minus a half, plus 2, minus 8/3, minus 2, minus 4. Summing all this up, you get 9/2. And that's the answer. Okay, this last problem involves revolving a function around the x-axis, and we'll be talking about that on Wednesday this week. Notice if we revolve this, we're going to get a solid. The radius of the disk, we're going to use the radius of the disk is going to be equal to 9 minus x squared. So the radius squared of x is going to be 9 minus x squared. So the volume using the disk method is going to be the integral from 0 to 3 of pi r squared of x dx, which is equal to pi integral from 0 to 3. Let's square the r, which is be 81 minus 18x squared plus x to the 4th. Dx. And when we integrate this, bringing it down here, we'll get pi times 81x minus 6x cubed plus x to the 5th divided by 5. Evaluating between 0 and 3, plugging the 3 in, we get pi times 243 minus 162 plus 243 over 5, and this equals, I believe, 648 pi over 5, and the answer is C.